Alright guys, this problem, it's a work energy theorem problem. We're going to set this up like normal. You got a mass, a car that's 1,500 kilograms. So we know that is mass. And the car's going to slow to a stop from 15 meters per second, about 30 miles per hour. And then it wants to know how much force in pounds is actually needed to stop the car. Sorry. So we're looking for force. And I'm going to separate these variables. Mass and force typically go together. Distances and speeds typically go together, so I'm going to kind of still put them in with my variables, but off to the side here. So you're coming to a stop. So VF is 0. You were initially going 15 meters per second, and it was over a distance of 15 meters. So again, my stuff in parentheses, well, 1 at the end is the answer, but in the other references are just what it is in our unit, so you can picture this thing. You're going about 30 miles per hour, and you come to a stop over 50 feet. Just how much force was required to actually stop your car. You could solve this with F equals ma. There's enough information here to find the acceleration, and then multiply by the mass to get force. That would work. We are on the energy chapter, so I am going to make you use the work energy theorem. After this chapter, you can go back to whatever way you prefer, but for this chapter, we are definitely going to use the work energy theorem, and that is written as, so W for work equals delta E, change in energy. And so work is going to be, delta E is going to be equal to EF, so final energy minus initial energy, like delta always is, final minus initial. So work is the push, right? That's what actually stopped the car, the push from the wheels on the road. The final energy. So to figure out how much energy you have, or what energy you have, we're going to come up here to the energy options, and we got, there are multiple possibilities for energy. We're focused on 4 right now. Either the object was pushed, that's W. UG, that's gravitational potential, is the object elevated? If you say yes, then you have to have UG in the equation. Is the object acted upon by a spring? That's US. If you say yes, then you have to have spring energy. Is the object moving? Then that's kinetic energy. So what was this car doing at the end of the push? Well, what was its final energy? It's just 0. Didn't have any of those, right? The car pushed it to the stop. I mean, the brakes and the tires did push it to a stop. We already have that. That's the work. And it didn't go up a hill. It was no longer moving, and it didn't hit a spring. So we have 0 final energy. Initial energy-wise, we ask ourselves the same 4 energy questions, options, whatever you want to refer to it as. So was it being pushed? It was. We already have that. So we've already concluded that it was being pushed. So we already have that. Did it start on a hill? Or elevated? No. So UG's out. Did a spring push it to get it started? No. Was it moving initially? Yes. So we change EI to K. Now, so if I had said yes to any of those other ones, I would put those in there for EF or EI. And you could have combinations. EI could be 2 things. What if you were on a hill and moving? Then it would be UG plus K. So just be aware, EF and EI can be any combination of those 4 things. Once we get this, so here's the equation. This is the important part. We're going to start writing this in terms of what it is. So we look up the equations. What's work? Well, it's force times displacement, 0, 0, minus K is just 1/2 mv squared. So now this is all set up for us to put our variables in. And again, it needs to be written. Make sure you're writing this out, and then tell me what those equations are. So again, you're just looking that stuff up. Well, after this step, you're just looking up the equations. But again, this is the equation part, most important. Then you write out what the variables, like what the actual equations are, and then we're going to do the setup where we plug everything in. So F is what we're looking for. D was how far the push happened, which would be the 15 meters. Here, just a review. We should check that all these units match. Meters, meters, meters were good. Seconds were good. Kilograms, fine. Like everything's metric and matches, so we're good. So it'll come out in the right units. The zeros, right, 0. So I'm just going to go -1/2 Mass is 1500. And then V squared, what did we say V was? 15. That's your final, so 15 squared. And then we would just divide both sides by 15. We're going to get force equals whatever it is in newtons. I don't know what that is. Then if you multiply by 0.225, the conversion from newtons to pounds, I should probably write this out. There's 0.225 pounds in 1 newton, which is the previous chapter, which we discussed in the previous chapter, the fourth chapter. That will convert it to pounds, and so our final answer will be, with sig figs, about 2,500 pounds. I'm not going to go through the calculation, but I mean, make sure you are writing in what the newtons are, and then you convert it. But I think you get the idea, and I will see you guys later.